Hello and welcome to my video about sequences and series word problems. So this is an addition to the Learning Guide 1 set of videos for my Math 20-1 YouTube playlist. Hope it helps. So we've got a bouncy ball that has a 70% efficient elastic collision. So if it is dropped from a height of 3 meters, what is the height after the 8th bounce? So basically it returns to 70% of its original height every single time. So what is the height after the 8th bounce? Okay, so this is what's going on. We're going to draw this out roughly speaking first so that we have some idea of what's happening. And this is a height versus time graph. So it's dropped from a height of 3 meters here, and it hits the ground, then it bounces up again to 70% of the original. So I don't know exactly what that is, but 2 point something, right? So then it bounces down, and 70% of that height, down, 70% of that height, down, okay, and so on and so forth. So I'm going to draw this out for 8 bounces, and hopefully you can get this sort of idea of what that looks like for the 8th bounce, and then we won't keep drawing for 12. So this is 4 bounces, 5, 6, 7, whoops, oh, that was not super great. So it's 4, 5, 6, 7, 8. And actually, this is kind of an interesting question. We could add a part D here. Maybe we'll get to it if we can at the end. Okay, so anyways, this is 8 bounces. Okay, so every bounce, it does 70% of the original. Just to give you some context, that would be 3 times 0.7. So our second bounce would be 2.1. The height, actually, sorry, to be very clear, that is the height after the first bounce, right? So it's after the first bounce. So in this case, it's after the 8th bounce. So we need to follow our formulas, which look like this. It's a geometric sequence, so it's going to be Tn equals T1 times R to the n1 minus 1, I believe it is. We can just double check quickly. Yes, indeed. So the real question is, what do you take as T1? Now, this is the height after the 8th bounce. So this is the height we're going to, or after the first bounce. So we're going to take that because we're looking for it after the 8th bounce. So 2.1 is T1 times R, which is the rate, so 0.7. And then n minus 1, so 8 minus 1. So T8 equals, and honestly at this point, all we do is we type it into our calculator. So like that, and then 8 minus 1, press enter, and you get your height. So this is in meters, right? So 0.1729 meters, because it started with meters. So I'm going to just say that is 17 centimeters. All right, what is the total distance traveled after 12 bounces? Now this is where it gets really difficult, because this is a series, this is a sum, the total distance traveled. So if we were just to think about what we just did before, we would be getting this value, this height here, right, plus this height here, 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 right? But that's not what we want. We need the total distance. So we need to actually double it. So we're going to need to add this red part in order to actually include the entire total distance traveled. So we're going to add this red part here. So let me just highlight it all the way down. Okay, now we're going to do it for 12 bounces. So it is going to be kind of the same process with our formula series of a series. So this is going to be Sn, but we're talking geometric series, which is going to be one of these two. We don't know Tn, so we're going to just use the top one there. Yeah, so T1 and then r to the n minus 1, and then r minus 1 underneath. Yeah, so that's our formula. So then we get Sn equals, and then T1, which is 2.1, and then the rate 0.7, but we're doing 12 bounces, so the n is 12, and then minus 1, and then the rate is 0.7 minus 1. So we can simply get this answer here, but it's not our final answer because of what? What do we have to change to get our actual final answer? Okay, so that is our value here, 6.9. And this is meters, right? But this is not our final answer because we also need to include that red part. So we are going to take that number and we're going to double it. So 6.9 and then times 2, right? Because we need to include both parts. So we're going to get 13.8. The up and the down. Is that our final answer? No, it's close, but not quite, because we have not included this part. And hopefully you can see based off my drawing of a graph here, that we need to include that part. So we're going to take that number and we're going to add 3 meters to it. So we're going to have 16.8 meters. Is that my final answer? Yes, it is. So be very careful when you read these questions because it could say after 12 bounces, it could say before or on the 12th bounce or before the 12th bounce. It really depends on the wording, so be very careful that you read these questions well. Okay, after which bounce does it reach a height of about 25 centimeters? Okay, so now we're going to work a little bit backwards. So it's still after a bounce, which is nice because then we can kind of keep it all the same. So 25 instead of the Tn. T1 is 2.1. R is the rate, so that's the 0.7. And then the n minus 1. Okay, now it's not going to be perfect here, but I think you'll be able to see the right idea. So divide both sides by 2.1, and we get 11.9. We get this, and minus 1 here. Okay, now there's really no good way of doing this unless the numbers are easy. So if the numbers were something like 16 equals 2 to the n, you could solve for n because 16 is 2 to the 4, right? So if 16 is 2 to the 4, then n must equal 4, right? But that's not what's going on here. We don't have easy numbers. So since we don't have easy numbers, we're kind of going to have to just guess and check a little bit. So 0.7 to the exponent, I don't know what it is, 8 minus 1. No, that's the 8th bounce, so it must be before that. So I'm going to say 6 minus 1. No, not quite. We have to get smaller than that. So let's try the 7th bounce. And and there it is. So it's not exactly right, but it's 11 point and then a high number, so it's close enough. So our value is when n equals 7. And the key is it says about, so that's why it's close, but not exactly. Ow. Okay, so that is an interesting question, but actually I just came up with a new idea here. So let me write it down. Okay, here is a weird question because it kind of seems impossible. But you can imagine that a ball will bounce and bounce and bounce and bounce and get closer and closer to the ground. And so at some point it basically has bounced quote unquote forever. So what would you do in this case? Well, here we're going to use an infinite geometric series. So we have s to infinity, and we have to just use that formula. So t1 over 1 minus r, and there's really nothing else you can say about that other than r needs to be less than 1, and in this case r is less than 1, so t1 is 2.1, r is 0.7, and so we would get a value of 7 meters. Okay, but is that our final answer? No. Again, same thing as before. We need to double it and then add 3. Right? So if you double it, you get 14. Then you add 3, you get 17 meters. So that ball, if left to bounce forever, will get to 17 meters. Now, our number is close to that because it's 12 bounces, but if you leave it forever, it should get to 17 meters. Okay, here is an interesting question as well. Let's try this out and see if you can understand it. If the sum of an arithmetic sequence is that, what is the common difference? Okay, so this is kind of a weird question because it's got a whole bunch of algebra involved. So it's the sum of an arithmetic sequence, which really means that it's the series. So the series is 4n squared minus 3n. Okay, now the formula for an arithmetic sequence, arithmetic series, is one of two options here. Now we don't know tn, we don't know t1, and we don't know d. So which one are we going to do? Well, we're looking for the common difference. So let's find that first one. N over 2. And then we're going to do 2t1 plus n minus 1 d, and then all in brackets there. Yeah. Okay, so this is now our formula. So we're going to just slowly solve this as far as we can. We can't solve it very far, but we can go as far as we can. So if we, we'll put some stuff together. So we're going to have 2t1 here. That's not going to change, but we'll put the d inside. So we'll have dn minus d. And then we'll put the n over 2 inside. So it'd be t1n plus d over 2n squared minus d over 2n. Okay, now that we have that, I don't know if you'll be able to see it quite yet, but I'm going to try to make it obvious here by making the n's all in red. Okay, and changing the order of everything so that it looks the same. So maybe you can see it already, and maybe not. And I'm actually going to factor out an n over here as well. so that it becomes even more obvious. What do you see? Well, hopefully you can see that there's there's an n squared on both sides, so that value must be equal. So the 4 must equal the d over 2. And also, actually, not that this is helpful quite yet, but the negative 3 must equal the t1 minus d over 2. Okay, so we're going to get to that in a second. That'll be useful in the next part, actually. So we can just write that down right here. Okay, it'll be useful there, but hopefully you can see that. Okay, so let's go ahead and solve this one. We're going to solve for d, so we're going to just move that 2 over, so d equals 8. Well, now that we have d equals 8, let's look at the second equation. What is the value of the first term? Well, we can put that instead of d, and we can solve for our first term. So it'll be negative 3 equals t1, which we don't know, minus 8 over 2. And we're just going to solve it now. So negative 3 equals t1 minus 4. We're going to move the 4 over. So t1 equals 1. All right, so it's just a bunch of algebra, but this is something interesting to notice here, because that n squared, it needs to work for any value of n there. Okay, so here's another interesting question. This is our last one for the video. Below, you will find a sequence of 3 squares with their widths given. Assuming the pattern continues, what is the area? Area of the 13th square? Okay, it's kind of a weird, interesting question. Just doing it with geometric shapes. But if this is the width, what's the area for this first one? 81. If the width is 6, what's the area here? It's 36. What's the width, the area here? 16. So you could look at the area patterns, or you can look at the width patterns. There's actually 2 sets of patterns here. So either you can look at 81, 36, 16, and that would continue, or you can look at 9, 6, 4, and continue. So either one works just fine. Basically, we need to find the rate. Okay, it's not an arithmetic sequence. If you look here, you can see that it's a rate. So it's going to be 36 over 81, which means it'll be 4 over 9 for that blue version. Or for this other one, it would be 6 over 9, which is 2 over 3 for the width version. So depending on what you're looking for, but that would be right. So assuming the pattern continues, what is the area of the 13th square? So let's use, you can use whichever one you want, but if you use we'll do it in both actually, just to show it. So we're looking for the area of the 13th square, so Tn, which is 13, equals T1, which is 81, times the rate, which is 4 over 9, to the n minus 1, so 13 minus 1. So T13 equals, and so now we can just type it in. So 81 times 4 over 9, and then 13 minus 1. And so we get this tiny little area of 0.0004, I think. Nope, one less 0. 4,811. Let's just leave it there. Okay. So that is the area of the 13th square. Now, if we do this with the green equation, we would kind of do the same sort of thing, and you'll see we get 9 times 2/3, 13 minus 1. So 9 times 2/3, and then to the exponent, 13 minus 1, and you're going to get this value, which is 0.069. 0.069. I'm going to say 694. Okay, so we have that value. So why are they different? Well, this is the width of the 13th thing. This is the area. So if you did it the green method, you would have to square that. So square that value to find the area. And watch, we're going to square it right now, and it should give us the same value. And look at that, it does. Okay. Okay, hopefully that makes a little bit of sense. We're going to try just this part B here. If the pattern continues to infinity, what would be the sum of all the squares areas? Well, this is going to be, just the sum to infinity formula. So it would look like this. T1 over R minus 1, I believe. Nope, 1 minus R. Okay, so it's going to be T1, which is 81, over 1 minus R, which is 4 over 9. And yeah, we could plug this in our calculator, or we can actually simply solve this by hand as well. So 9 over 9 minus 4 over 9, which is going to be 5 over 9. So 81 over 5 over 9, which means it's going to be 9 times 81 over 5. Okay, so 9 times 81 divided by 5, and we get 145.8. Okay, and like I said, you could, if you have a nice calculator, plug all of this in all at once and avoid kind of making those sorts of accidental mistakes. But this would be, another way of doing that. And actually, if you want to have a decimal answer, you can see that it's exactly the same. There you go. So I hope this video helps you better understand some of these sequences and series word problems. They can be very challenging, but as long as you take your time, look at it carefully, I think you can do it. I hope this video helped, and good luck.